So I read the timeline in the last podcast. Let's read a few more details. You want to know what has been happening. So we won't go into all the details, and in fact we don't even know all the details, right? You remember how we derive our past information about the climate, the geology, the chemistry, the biology, the greenhouse gases, and so on and so forth. And there are many details. If you want to know what happened in the last 10 years, you may find information. Some instrument is measuring something, some satellite is measuring something, maybe what happened every day in the last 10 years. But if you go 100 years, maybe you know only what happened every month, because you don't have daily information. If you go back even further, you may find what happened every year, because you don't have seasonal information. So if you keep going back, maybe you only know what happened every 10,000 years, every 100,000 years, and so on. So the old information is not stored at a very high resolution in time, it's called, but you are too young to know what that means. Basically that means, is it available let's say you are 10 years old. Do you remember everything from your childhood? Do you remember every day? Maybe you remember what you did yesterday or day before yesterday, but if you want to think about what happened last year, you may only remember approximately what happened every month or so. Anyway, so when we do this for the old Earth, this is what we have to remember, and it's approximately here in the information we saw before, right? So you can see that the curve seems very smooth here. There's a big jump here, little jumps, and then you get more wiggles here, you get many more wiggles here, and so on. So that means here you are only getting information every few million years, etc. If you don't understand it, do not worry about it. Let's just read on. You might think your mom and dad are old, that the pyramids are ancient, or that the dinosaurs you can see at the Natural History Museum in the US or some other museum in your country are the oldest things ever. They were there for a long time ago, but all of those are nothing compared to the age of the Earth itself, which we mentioned in other sections as 4.6 billion years ago. This book keeps saying 4.5 billion years, which means basically there's some uncertainty. You are not sure. That's about 10 times as old as the first trilobites that swam in the oceans that we talked about before. It's the primitive algae that was doing some photosynthesis. 100 times as old as the Himalayas. Himalayas are very old. More than 1,000 times as old as Lucy, which was found just about 3.2 million years ago, or at least she dates back to 3.2 million years ago. She was found very recently. That was one of the first humanoids. We are humans. Humanoids are those who are related to us, but they are not exactly Homo sapiens. 10,000 times as old as the saber-toothed tigers in their heyday. 100,000 times as old as the first rock drawing that humans made that we just mentioned in the last podcast. 1,000,000 times as old as the Egyptian pyramids, right? Nearly 10 million times as old as Mona Lisa, right? Da Vinci there. And around 100 million times as old as your mom and dad. 100 million times as old as your mom and dad. If you keep thinking your mom and dad are old, now imagine something as old as 100 million times their age, and that's old. So I bet your mom and dad have changed quite a bit over the years. They probably look way different. You may not remember, you may be very young, but if you ask them to show their photos, let's say before they got married, when they were kids, and then they'll be saying, oh, you just look like me when I was a kid, and so on and so forth. So we age and we look different, right? So you can say they probably look way different now than they do in their childhood photographs. The pyramids have changed a lot over the course of time too, even though they're standing firmly against all the climate change and the little ice age and the medieval warming. If you don't know what that means, don't worry about it. They have worn down to the point where there is almost nothing left of some of these pyramids. The trilobites died out long time ago, and so did the saber-toothed tiger, but from fossils and so on we know that they did exist. Now trilobites don't leave any fossils, but they leave imprints on the rocks and so on and so forth. In the same way, the earth is no longer what it once was. Over many million years it has continued to change and evolve. 100 million years ago, America and Europe were attached to each other. At that time Australia was not an island, but India was already floating around. Mountain ranges have come and gone, they form and they die away with the plates moving. Earth was once entirely covered with lava and once completely under snow and ice, as we'll read a bit more, and we discussed this before as Snowball Earth. The water in the oceans was sometimes higher and sometimes much lower than it is now, which means land was higher and lower as well. The layer of air around the earth has not remained the same either. There was a time when there was much more oxygen in the air than there is now, but also a time when there was no oxygen in the air at all. It was in the ocean but not in the air. What happens if oxygen increases to a much higher level than now? What does oxygen do? When of course we breathe it and plants release it with photosynthesis and so on, but oxygen is consumed when we burn something like the fossil fuels we are burning, and we can increase, we can measure the increase of fossil fuels. We can also measure the decrease in oxygen because we are burning so much of it. Nothing to worry about because there is plenty of oxygen. But the point is, if you increase the oxygen much more, let's say by 10%, then everything will burn up much more easily. Right now a wet plant may not burn easily, but if you increase the oxygen, then everything becomes much more combustible. So life obviously depended on oxygen coming out from the ocean into the atmosphere and decreasing along the way as well. We have now evolved to live in this oxygen. Sometimes when you feel winded, sports people, when they run fast, sometimes they put a mask and breathe oxygen to get the energy back. Or if you go climbing mountains, you feel the oxygen levels drop and you have trouble breathing and you get this altitude sickness and so on and so forth, right? So it's good to be aware that the earth is constantly changing. This is true for land, for the water, and for the air as well. And so it is true for climate too. And if plants are taking up CO2 and releasing O2, then you know that as plants evolved, as we mentioned before, they would have changed climate, and in fact they did, right? So let's look at the first 2 billion years now, when we have nitrogen, methane and CO2. Methane, why are we mentioning it? When the earth had just recently come into existence, some 4.5 billion years ago approximately, it was really hot. There was magma, there was volcanoes, the plates were not yet completely formed, there weren't any thermometers or weather forecasters around to measure just how hot, but we can approximate it with all the other detective work we can do. So it got up to around 2000 degrees Celsius. 2000 degrees Celsius. It was so hot that the outer layer of the earth was completely melted. Our planet was one big ball of lava. A lot of meteorites were crashing, and moon would have formed much later by some other little planetoid crashing into us and taking a piece of the earth out, and so on and so forth. The thin layer of air developed around the earth, the atmosphere formed, the air did not yet contain any oxygen, the wonderful gas that we breathe in about 1,000 times an hour. That's oxygen. But Our atmosphere did have nitrogen and methane and carbon dioxide. Now we talk about methane and carbon dioxide as greenhouse gases, and there was much more methane than carbon dioxide. That the last one is a bit of a mouthful and it gets mentioned a lot, so we have to shorten it to CO2. Carbon dioxide is CO2, you already know that. So like the scientists always say CO2, they don't say carbon dioxide each time. It's pronounced CO2. Methane and CO2 are very good at holding on to heat. That's why it was so hot on Earth. The atmosphere worked like a greenhouse. You know what a greenhouse is, right? It's a little glass or plastic house that allows sunlight to come in. You grow things inside it. It doesn't allow the water to escape and keeps some of the heat and makes the weather inside the greenhouse more steady. You know, right now when I went to have coffee in the morning, it was sunny and now it's cloudy and maybe it's drizzling now already, okay? But in the greenhouse, such changes do not happen. So the atmosphere worked like a greenhouse gas, one of the glass buildings where plants and vegetables are grown. The glass lets in the sunlight and keeps the heat for a very long time. So this greenhouse effect makes the planet nice and warm, but it is possible to have too much of a good thing, which is what we are doing now by increasing the greenhouse gases which trap the heat and making the blanket that covers us from being so perfect to becoming too warm. And we are looking here at the sun's energy coming in. Some of it is getting reflected by the snow and ice, and some of it is getting taken up by the ocean by heating the land, melting the glaciers, evaporating the ocean, and then it is trying to go out. But we have this blanket which is bouncing it back and not allowing it all to go outside. This is what the blankets are for, to make you warmer. In the early years of our planet, it was like hell on Earth, a temperature of 1,000 degrees, thousands of degrees, in fact, volcanoes erupting all over the place, a sea of stinking lava and air that was too toxic to breathe, because when you have so much lava, you have sulfuric acid and ash and all sorts of chemicals, methane and so on. But there was worse to come. A bombardment of meteorites kept hitting the earth for 100 million years, and in fact hundreds of millions of years. Huge rocks and blocks of ice fell from space onto our planet. The ice melted and evaporated. As a result, the air came to contain more and more water vapor, water in the form of gas. You can't see it, but it's all around, even you know that. And it's there even now. Hydrogen and oxygen, they can be split when it's too hot, but they can combine to form water as well, and when it's hot enough they stay as water vapor. Nice monsoon has arrived, and you probably can hear the rain in my recording. I'll see if the recording is affected by this loud noise of the rain, but it's beautiful. The water cooled the surface of the earth a lot, taking it down to around 200 degrees. Many places the lava began to harden, and hard lava is, yes, that's right, hard lava becomes a stone, right? That's how the crust we live on was formed. The land that we call, and the ocean has a crust at its bottom as well. The ice of the meteorites was still melting, but it didn't all evaporate. Liquid water filled the oceans, and the water vapor became the first rain. We have rain there, and I'm talking about rain here. The story of where the water came from and how quickly the oceans formed and so on is still some detective work going on, but we keep learning as the geologists and the geochemists and the other scientists keep digging and finding new evidence. Okay, so we'll leave it here and we'll come back and read further on how the earth evolved from 4.5 billion years and continue to the discussion of where we came along and what we started to do. And is it a good thing or is it a bad thing, and how bad is it? What can we do about it? All these things we'll discuss as we go along. Okay, we'll come back and discuss more of the earth's history, old earth. Okay, see you in the next podcast. Kids,